กดบันทึกแล้ว Okay, so we start recording our today's lectures. Okay, today we are going to talk about the frictions and lubrications. Right. We will first talk on the frictions, and then we will talk on lubrication later. Okay. In the heat transfer for the internal combustion engine, right, we have already mentioned that frictions take into account for about 10% of the heat input to the engine. Right? These frictions come out from both heat and mechanical motions in the engine. Right? And because of the mechanical motions, right, frictions can deteriorate the cylinders and other components in the engine. Right? And that's why the engine needs lubrications in order for the engine to run at the safe operating conditions. And one good lubrication is the oil, the lubrication oil that can help reducing the frictions. Okay. The work that come out, no, okay, frictions, okay, frictions can also reduce both engine powers and its efficiencies, right? And that's the reasons why we cannot get the brake work equal to the indicated work from the engines as shown in these equations, right? That you can see that the friction work is equal to the net indicated works minus the brake works. Okay. To find out the amount of the frictions, right, it is best that we need to measure the mean effective pressures, right, in terms of the frictions mean effective pressures. To find out the work, right, to find out the work that come out from the engines, right, we can determine from the mean effective pressures times with the displacement volume. This is in general, right? If we want to find the amount of works, right, and the power from the engine can be found from timing the work, right? The MEP time the displacement, timing the work with the engine speed divided by the number of crank revolutions in here, right? So the frictions mean effective pressure, right, can be found in the same way as shown in these equations, the same way, right? So if we know the friction powers, we know the speed of the engine, we know the displacement of the engines, then we can determine the friction mean effective pressure, right? From these equations, you can see that the friction mean effective pressure is mainly depend on the engine speed. By knowing that the friction mean effective pressures depend on the engine speed, right, then you can write down the relationship between the frictions and the engine speed in terms of the quadratic formula as the one that I show here. This is one formula to determine the frictions mean effective pressures, right? And in the quadratic forms, right, to the speed of the engine to the power 2, right? N represent the engine speed, right? The constant A is a constant due to the boundary frictions that happen, right, because of not enough lubrication. So that means if the engine have not enough the lubrications, the letter A here, this constant will be high. Okay. And the letter B is a constant due to the engine speed and related to the hydraulic shears, right? Hydraulic shear, because the constant B is related or time with the engine speed, and the velocity of the lubricant which determine the hydraulic shear depend on the engine speed. Let us see another constant, right, with time with the engine speed to the power 2, right? This is the constant due to the engine speed square, right? This constant is for accounting for the losses that come out from the turbulent dissipations during the flow in the intake and in the expansion flow. So what is we call the turbulent dissipations? The turbulent dissipations that we mentioned is the conversions of the viscosity in the mechanical energies to heat in the shear flow, which normally happen during the intake and in the expansion stroke, right? So it's a conversions of the viscosity in the mechanical energy to heat, right, when the shear flow happen. Right? Shear flow happen because we have lubrication flow or the lubricant flow, right, in the engine. Okay, so let's look at the pictures, this picture, that how we can calculate the frictions that happen, right, from knowledge that we learn from the fluid mechanics, right? I think most of you should already be familiar with this picture that you learn in the fluid mechanics. This is the flow between two parallel plates, one at the bottom and another one at the top. Right? This kind of flow have many applications, right, in engineering. Okay, and we are going to apply this concept to our engines, right? By we will take this bottom plate, right, the bottom plate here, as our cylinder surface, which is fixed, not moving, and the top plate here, right, is represent our piston surface that is moving, right, and we can move left or right here. Okay. And in the middle here, right, which we consider to be our boundary layer thickness, right? Or in fact, it's a clearance between the piston, our piston here, and our cylinder here, right? Inside here, we have a lubricant or the lubrication oil that flow in between these two plates, right? So one plate is moving, one plate is fixed. So the velocity profile of our lubrication flow look like this, right? Where the velocity is 0 at the bottom. Our velocity, our lubrication velocity is 0 here because this plate is fixed. Our cylinder wall here is fixed, right? And at the top, the velocity of our lubrication oil here, right, is equal to the velocity of the piston. Okay, and by using this velocity profile, right, we can calculate the shear state, right, due to this flow, right, from these equations. Okay, and this is the shear stress that we can calculate from the flow behavior here, right? Shear stress is equal to mu, which is the dynamic viscosity of the lubrication oil or the lubricating oil, and du by dy, right, is the velocity gradient between these two surfaces. Okay, or in other words, it is the change of the velocity, right, along the current, right, along the distance here, delta y here, right, between these two surfaces here. Okay. Okay. So from this shear stress here, we can calculate the amount of the frictions, right, because it is the force due to frictions divided by the piston surface area, right? So we first can calculate from the behavior of the flow, which is inside this current area here, right? And then we relate this flow behavior, right, to find the friction force, here. Okay. So let's look at the examples. We have a 5 cylinders and inline engines that has a 8.15 centimeter bore and a 7.82 centimeter stroke, right? And we have a connecting rod length of 15.4 centimeter, right? Each piston inside the engines, right, have a skirt length of what? 6.5 centimeter, right? And the mass of the piston is 0.32 kilogram, right? Now, at a certain engine speed and crank angle, the instantaneous piston speed is 8.25 meter per second, and the clearance between the piston and the cylinder wall is 0.004 millimeters, right? The SAE 10W 30 motor oil is used in the engine, right? So this is the type of the lubrication oil that used in these engines, right? And the temperature of the piston cylinder interface, right? That means the temperatures, and at the temperatures of the, the clearance area here, right? The dynamic viscosity of the oil is 0.006 Newton second per square meter, right? Because the dynamic viscosity change with the temperatures, right? That's why they mentioned that at this temperature, the dynamic viscosity of the oil is 0.006 Newton second per square meter. Okay, let's calculate the friction force on one piston at these conditions. Okay, so we have piston move inside the cylinders, and we have the current area between the surface of the piston and the surface of the cylinder. And this current area fill up with the lubrication oil, right? So every time that the piston move, right, it also take this oil to move with the piston, okay? So it creates the hydraulic shear because of the flow that happened in the current area here, right? So this hydraulic shear, right, can be calculated from these equations, right? We know the dynamic viscosity, they already given, right? We know the change of the velocity, right, from 0 to the velocity of the piston, right, with it 8.25 meter per second, okay? And the clearance, the distance of the clearance between the piston surface and the cylinder surface is what? 0.00004 meter here. This was given, right? So all of this information in this formula already given, right, in the problem. So we can calculate the amount of the hydraulic shear, which is 12,000 something Newton per square meters, right? Then this hydraulic shear is equal to what? The friction force divided by the surface area of the pistons, right? So we need to calculate the surface area, which is the contact area between the piston and the cylinder wall, right? Which is what? Pi times the bore of the cylinder, which is the diameter of the piston, times the height of the piston, which is referred to the skirt length of the piston, right? So this will be the surface area of the piston, right? That we have the lubricant oil attached to this surface. So the friction force that happen on the piston, right, can be calculated from this hydraulic shear. Right? We said it's hydraulic shear because it's the shear stress that come out because of the flow. Right? So hydraulic give us a sense of there is a flow, and this flow create a shear stress. Okay, so we have the hydraulic shear stress times with the piston surface area, and this become the amount of the friction that happen, okay, to our pistons and cylinders here. Okay, so that is how we can calculate the friction that happen by using the knowledge from fluid mechanics, right? By calculating the hydraulic shears, okay, and then relate this shear stress to the friction force. Okay, so from the examples, right now you can see that we can also relate the friction force or the friction mean effective pressure, right? Friction force or friction mean effective pressure to the mean piston speed, because in our previous examples, they talk about what? Not the velocity of the flow, but the piston speed, right? So we can relate the friction mean effective pressure to the piston speed like this, okay, where this A prime is the same constant A, right, due to the boundary layers, as we mentioned earlier. And this B prime, right, is also related to the constant B, right, but it have to be divided by 2L, okay, right, where L is the piston stroke, and C prime, right, related to the constant C, right, divided by 4L squared, right? So this equation is kind of changing from the engine speed to the piston speed, right? And the relation between the engine speed and the piston speed are related together by the piston stroke, and that's the reason why the constant have to be divided by the piston stroke here. Okay, so for the number, right, the number or the magnitude of the frictions, right, in general, the friction mean effective pressure will be about 10% of the indicated mean effective pressures. At what engine conditions? When the engine under wide open throttle, right? Wide open throttle, that means under the heavy loading on the engine. So we have to open the throttle, right, widely, okay, wide open throttle. So under that conditions, the friction mean effective pressure is about 10% of the net indicated mean expression, mean effective pressures, right? And this friction amount will keep on increasing, right? If the engine load start to reduce until at the idling conditions, right? At the idling conditions, right, the frictions become 100%. Why? Because at idling conditions, there is no output come out from the engine, or there is no brake power is taking off from the crankshaft, right? So the engine run without loading, right? So friction become 100%, right? Because there is no brake powers, right? So you can come back to these equations, right? If we have no where power come out, right? The work from the frictions will be or equal to the net indicated works, right? So that means 100% in here. Okay. Yeah. Now, to find out the friction loss from the engine, we can do it by using the electric motor to drive the engines by we first running the engine at 5 mode. At 5 mode means we run the engine as it used to be run, right? We have ignitions, right? We have firing in the engine. This is what we call the fire mode, or in the actual operations, right? And then after the engine reaches its steady state, right, we then turn off, right? We turn off the engine, right? And after we turn off, we immediately run the electric motor, here, right? The reason we do this is we want to avoid the effect of temperature, right, that happen to the engine fluid. We don't want anything to change. That's why we immediately run the electric motor, right, in order for this electric motor to run the engine after we turn off the engine, right? So in overall, just want to keep the engine conditions as close as possible to the condition of the normal engine operations, right? And then we will measure the electric power that we supply to the electric motor, right? And the amount of the electric power that we supply to the electric motor will represent the amount of the friction power, right? So it will, we run the engine under normal operations, and then we turn off the engine, and immediately or suddenly we turn on our electric motor and use this electric motor to run the engine. Okay, and then we measure the electric power supply that we supply to the electric motor and use this amount of power, the electric power, to indicate the amount of the friction powers. Okay. This graph shows you the friction losses, right, in each component, right, measured by motoring the engine, right? Motoring the engine, that means no fly engines. Okay, right. We run the engine by using the electric motor, and we calculate the friction loss, right? So in this graph, you can see that all losses, no matter that it happened to the valve, the piston and ring, the oil pump, the water pump, and the alternator, right, and the crankshaft, all these losses increase with the engine speed. Okay, and if you look closely, the highest amount of the friction loss, right, is happen at these two, right, the valves and the piston and rings, right. For other components below here, such as the pump, the oil pump, the alternator, right, the friction loss are considered to be small when compared with these losses that happen at the valve and the piston. Okay. Now, if we take a closer look at the friction loss at the piston and the piston ring, where we see that the friction losses is significant, right? What we found is that in overall, right, there is no much difference in friction loss or friction force, right, that happen during the intakes or compressions or the exhaust stroke, right? Even though that pressure and forces during the compression stroke are greater than the other stroke, right? So we know that during compressions, the pressure and forces are greater than air. Normally, we expect that the friction losses that happen to the piston and the piston ring, right, mostly will happen during the compression stroke, right, because pressure and force during that stroke are greater than other stroke. But in fact, we see what we found is that the friction force are more or less the same, right? The friction forces in the piston are more or less the same for the during the intake, during the compressions, and during the exhaust. Because of what? Because frictions depend mostly on the engine speed or the piston speed, not depend on what actions that the piston is doing. Okay, so it depends on the speed only, right? So that's the reason why in whatever stroke that happen to the engine, the friction force that happen in the piston are no difference. Okay, for the numbers of the friction force or for the value of the friction force, right? The amount of the friction force on the pistons can be as much as what, 55% of the total friction force in the engine. Okay, and in the piston ring, right, it is about 20%. Okay, now as the engine speed increase, right, the amount of the friction force also increase, and it would be dangerous if the speed is greater than 15 meter per second, right? So if you remember in our very beginning lectures, right, we talk about the speed of the piston, and we have the recommend value, right, in the table, that the speed of the piston for different kind of engine should be this and this, right? And in here they mentioned again that if the speed greater than 15 meter per second, right, the friction force become dangerous, right? So that is the reasons why it is important that we need to study the forces in the piston, right? The forces in the piston, right? To see the behavior of the force in the pistons. Okay, so let's look at how we can analyze the forces on the piston. Okay, in these pictures, I will show you a piston here, right? You can see several forces acting on the pistons, right? For example, the side touch force here, right, that apply on the side surface of the piston, the gas pressure here that apply on the top of the piston, the friction force here, right, that also apply on the side surface of the piston, but in different directions from the side touch force. And this friction force can have the direction in the up and down directions, right, according to the piston motion here, right? And the last one is underneath here, right? It is the connecting rod force, FR here. Okay, so we have several forces that acting on the piston, right, during the piston motions. However, some of the force here are considered to be the reaction force, right? What does it mean, the reaction force? It means that these forces, right, if it's a reaction force, will happen only if there is a motion, right? So only when piston is in motion, this force will appear, right? And if there is no motions, this reaction force will disappear, right? They will not happen. Okay, for example, let's look at what are the reaction force. For example, this size such force is considered to be the reactions because it happened when this piston is in motion, right? And this size touch force, right, will act to the connecting rod here. Okay, so in other words, this connecting rod force, right, if it move or it in motion, right, so the piston in motion, it will create the reaction called the side touch force here. Okay. So this is the meaning of the reactions. Okay. This side touch force is not a constant force because of forces applied to the piston by the connecting rod here. Right? It is not constant and change with the directions. Right? And this side touch force also change with the accelerations, with the pressure inside, and also the friction force. Right? If you draw the free body diagram of the piston, right, they are all related. Okay, so the piston move faster, the side touch force change. The combustion happen heavier, the pressure inside the piston change, the side touch force change, right? And the friction force change due to the piston motion change, the side touch force also change. Okay, so all of these forces are vary during the engine cycles. Okay, another reaction force is the friction force. Right, friction force is a reaction due to what? The piston sliding motions. Okay, so when piston move, the sliding motion of the piston happen, and then the friction force happen. Okay. Okay, now let's look at, since we already know what kind of forces that happen to the piston, now let's look at the piston force analysis. Right, start from the x directions, in the x directions. Right, we have the summation of the force in the x directions, right, which is equal to what? The mass of the piston times with the piston accelerations. Right, this also equal to what? Equal to all forces that act on the piston in the x directions, such as what? The connecting rod force in the x directions, the pressure force with already in the x direction. Okay, the x direction is here, and the y direction is here, right? So we set our coordinate like this in our piston. So our x direction is in the vertical direction and y direction is in the horizontal one, right? So the force in the x direction is the connecting rod force, the component of the connecting rod force in the x directions, and the pressure force with totally in the x directions, and plus and minus of the friction force, right? Plus and minus because it depends on the friction motion, the direction of the friction when it moves. Okay. Okay. So in order to closely determine the sign of plus and minus that we just mentioned depend on the direction of the piston motion, right? We can also determine the sign plus and minus on the friction force based on the crank angle, right? The crank angle here, right? The crank angle represent here, oh here, down here. The crank angle is shown right here, theta. Right? If the crank angle is in between 0 to 180, right, the friction force is minus sign because the direction of the friction force is moving up, go up, right, again the x direction here. And if theta is 180 to 360, right, the sign on the friction force is plus because the friction is in the same directions of x. Okay, so this is the force in the x directions, right, that we can come up with the equation shown in here, right, from our force balance in the x directions. How about in the y directions? In the y directions, we have no motions, right? So x is in dynamics, but y is in static, right? So there is no motion. So the force balance become what? The summation of the force in the y direction becomes 0, right? So it will be equal to what? The component of the connecting rod force in the y directions minus the side thrust force here, right? So we have two equations. We have two equations. Friction force we can determine from what? We can determine from the hydraulic shear, right? We can use that to determine the friction force. The pressure force can determine from the combustions, right? And the side touch force can be what? Determined from the connecting rod force. Or the connecting rod force can be determined from the side touch force. So these are two unknown, but they are related with each other on the summation of force in the y direction equal to 0, right? So by solving this summation of force in the y directions along with the x direction shown here, right, you can find the side touch force according to this equation, right? If you know the mass of the piston, you know the accelerations of your piston, you know the pressure in your combustion chamber, you know the friction force, right, from the behavior of your lubrication oil or the hydraulic shear, right? And you know this phi, right? Phi is this angle, the connecting rod angle that make with the vertical line here, the center line of the cylinder here, right? Then you can determine the side touch force, right? And that means you can determine the connecting rod force here. Okay. Okay. So this is the force analysis in the piston, right? The force analysis. We have side touch force, we have connecting rod force here, along with the frictions and the pressure force. Now, from the summation of the force in the x directions, or from the force equation that shown in here, right, with equal to the mass of the piston and the acceleration of the piston, right? So from these equations, right, it shows that if we can reduce the piston mass, right, so we make our piston go lighter, right? That means we will have the less inertia, right? Less inertia, and the force in the x direction is reduced. That means we also have the less acceleration, right? If the mass of the piston reduced. Okay. Another thing that we should notice is in this picture, right? In this picture that show you the oil film thickness, right? Along with the crank angles, right? From this picture, you should notice that at the top dead center and at the bottom dead center, right, the oil film thickness is smallest or very small, right? small. Why? Because when the piston move down to the bottom dead center, or it move up to the top dead centers, right? The oil or the lubrication oil, when we said the oil here in this lecture, it always mean the lubrication oil is not the fuel. Okay, the oil here is squeezed out, right, when the piston is at bottom dead center or the top dead center, right? That is one reason. Another reason is at these positions, no matter it's the bottom dead center or the top dead center, the piston start to change its directions. Right? The piston start to change its direction. So the oil film thickness becomes small. But at other positions along the way that the piston move, right, the oil film thickness is always higher than this. Right? And it can be in the direction of increasing or decreasing. Okay. Okay. So let's look at the example of how to calculate the force in the pistons. Okay. At the conditions given in the previous examples, the engine performs a power stroke in the cylinders. Right. So that means we now have pressure acting on the top surface of the piston, right, because it's in the power stroke or the expansion stroke. And the crank angle is shown here with theta here and phi here. Okay. So at this point, the pressure in the cylinder is 3200 kPa, right? And the compressive force that happened in the connecting rod because the piston is moving down. So the force acting on the connecting rod will be a compressive force, right? Is equal to 8.1 kilonewtons. Right? Since this connecting rod force, since this connecting rod has a force, so the side touch force happen. So they want us to calculate the side touch force on the cylinder wall at this time, right? The information that they give is what? The connecting rod length is 15.4 centimeter and the stroke length is 7.82 centimeter, right? The crankshaft offset is 1/2 of the stroke length. What is the crankshaft offset? To remind you, this is what we call the crankshaft offset here. This distance, okay, is equal to 1/2 of the stroke length. Okay. So to find the side touch force, right, we know the connecting rod force, right? So we can use this equation, the summation force of force in the y directions, right, to find out the side touch force, right? But we have to find what is the phi here, right? So to find the phi, we look at this triangle. This is the length of the connecting rod. This is the crankshaft offset, right? And the crankshaft offset is half of the stroke length. Okay, so the stroke length is what? 7.82 divided by 2, right? So it's equal to 3.91, right? The crankshaft offset here. So this is 3.91 and this is the stroke length, right? The stroke length here, right? So the angle between the connecting rod and the center line here of the cylinder will be what? Tan phi is equal to 0.2539, right? So the side touch force will be equal to 1.994 kilonewton, right? If the connecting rod force is equal to 8.1 kilonewton. Right? So we can also find the side touch force by using another equations that we solve from combining the force in the x direction and the y direction all together. right? The previous one, we just only use the summation of force in the y directions, but this one is come up because we combine the summation of force in the x directions and in the y direction together. Okay, so we have to find first, if we want to use the equations, we have to find this term, the mass of the piston time what? Time the inertia, the acceleration of the piston, which can be found from what? Summation of force in the x directions, right? We know the connecting rod force, we know phi here, we know the pressures, right? And we know the frictions, right? This is come out from our previous examples, right? We know the frictions from our previous example. So we can find the inertia force. The whole term here is called the inertia force, which is what? 8,000 something Newton, right? So we just replace this inertia into these equations and calculate the rest, right? We can find a side touch force, right? Which is what? 1.994 kilonewton. Compared with the previous one, it have to be the same. Okay. So that is all about the frictions, right? The friction force. We know where the friction force happen or the friction loss happen, right? We can find out the friction force, okay, that happen in the piston because the friction loss mostly happen in the piston and the piston ring and also in the valve, right? And we phrase that if our piston speed greater than 15 meters per second, right, our friction force become dangerous. So we have to analyze the force in the piston, right, in order to avoid any dangers that will happen to our engine under high speed. Okay, so under high speed, right, not only the performance of the engine that you need to calculate, you also have to calculate the friction force that happen to the engine under high speed operations. Okay, so is there any questions from the friction before we go into the lubrications? If not,
No, huh?
then we will move on to the lubrications. Okay. The lubrication process is an important process, right, for good engine operations, right, because this process will help reducing the frictions. Okay. So what are the purpose of the lubrication system here? Right. The first one, of course, is to lubricate. In order to reduce the frictions, right, by having a thin film in a clearance area between the moving parts, which is the surface of the piston and the surface of the cylinders, right? This is where the frictions mostly happen. Okay, so to reduce the friction in this area, that is the first purpose. The second purpose is to seal, right? To seal, right? In order to form a seal between the piston ring and the cylinder wall, right? In order to reduce the leak of the internal oil, right? The lubrication oil, that result in the blue smoke at the tail of the exhaust pipe. Right? Because if our lubrication oil, which is the internal oil, leak out, right, it will create a smoke out from the engine. This is what we call a bobine here, right? A bobine here. So whenever you see the blue smoke come out or the white smoke come out, sometimes, right, from the exhaust pipe, that means you are losing your lubrication oil because it leak into the combustion chambers. Okay, so lubrication itself will help to seal itself, not to leak into the piston, into the combustion chamber. The third one is to clean, right, by picking up the metal particles and carbon, right, and then bring all these particle and carbon back to the oil pan, right? Because the lubrication oil is always circulated throughout the engine, right? So no matter where it goes inside the engine, at the end, it will fall down to the oil pan here. Okay, so everything that comes with the lubrication oil, right? Everything that comes with the lubrication oil, right? Finally, it will come down to this oil pan here. Okay. Number 4 is to cool down the engine, right? Is to cool down the engine by picking up the heat. The lubrication not only reduce the frictions but also picking up the heat and bring the heat back with it, right, down to the oil cooler pan, right? So this is the oil pan, and sometimes they call it oil cooler pan, right? To keep up some of the heat here, right? Because around here we have the air flow around, right? So it transfers the heat to the air, right? So in this picture here, right, you can see that the lubrication oil here is pumped to the top, right? And then it's passed down to the oil pan that below here, and along the way, it will pick up the metal particle and heat and bring all this back to the oil pan below. The other purpose of lubrication system is to absorb the shock, right, when there are heavy load imposed on the bearing of the engines, right? Because the lubrication oil here help to cushion the load or relieve the load that acting on the bearing. Okay. The lubrication oil can also absorb the contaminants, right? Because inside the lubrication oil, right, in the lubrication oil itself, right, we have some additive. We add some additive into the oil, right? So it can help absorbing the contaminants that enter into the lubrication system, right? Because we add the additive, and this additive can help absorbing all the contaminants, right? And that enter to this oil. Okay, so let's take a look on the type of the lubrication system, right, that used in the engines, right? The first one we call is the petrol or mixed lubrications, right? We call it petrol because this system we will mix the fuel or the petrol and the oil together. This oil is the lubrication oil, right? This petrol is the fuel. So we mix the fuel with the oil together. That's why we call it the petrol or mixed lubrication. Okay. This is the system that used when the crankcase lubrication is not suitable, right? That means our crankcase here below cannot perform as an oil pan, right? We cannot store the oil in here, right, inside the engines, right, because it's not suitable, right? Such as what? In the two-stroke engine, right? For two-stroke engine, right, normally we don't have the oil pan. We cannot the oil pan because the air fuel mixture is normally, right, in the two-stroke engine. The air fuel mixture is normally compressed in the crankcase, right? So it is impossible to have a lubrication oil in the sump down here. Okay, so that's the reason why we have to mix the oil with the fuels, right? Especially for the two-stroke engine. Okay, so the way the system works is what? The oil will mix with the fuels, right? And the ratio is usually about 2% to 5%. Right? That means in overall, we have 2% of the oil in 100% of the oil and fuel mixtures. Okay. Then this oil and fuel mixture is inducted through the carburetors, right? And then after the fuel is vaporized, right? Because in the carburetor, we inject the fuel to mix with the air, right? So the fuel is vaporized and mixed with the air. So it leaves only the oil, right? We separate, we mix the fuel and the oil. And when it falls into the carburetor, the fuel is vaporized, right? So it's separate from the oil, right? So leave only the oil in the form of mist. Oil is not evaporate, right? So oil is in the form of mist that flow via the crankcase into the cylinder, right, to do the lubrication for the main bearing, for the connecting rod bearing. Okay, so this is how we can do the lubrication in the case that our crankcase or the engine crankcase cannot store the lubrication oil. So we mix the lubrication oil with the fuel and let it flow to the carburetor, right? So the fuel will be vaporized, mixed with the air, go into the cylinder, but the oil, right, will not vaporize, right? So the oil in the form of mist will fall into the crankcase and do the lubrication, right, for the main bearing of the crankcase and also the connecting rod bearing. Okay. Other portion of the oil, right, will also go to lubricate the piston ring, and also the cylinders. Okay. The advantage of this system is what? It's simple. Simplicity. It's very simple, right? And it also have a low cost because it does not require what? Oil pump, filter, oil filter, and others, etc. Right? So you don't need anything, right? So the system is very, very low cost. Yeah. But the disadvantages are what? The disadvantage is that the system can cause the heavy exhaust smoke because the burning of the lubricating oil, right? Due to what? Due to when fuel vaporize, it might bring with it some of the lubricating oil or lubrication oil, right, to mix with the air, right? So this oil, when it fall into the combustion chamber, it burns, right? So we can see the heavy exhaust smoke come out in that case, right? It can also form the deposit on the piston crown or on the top of the piston and also in the exhaust port, right? If it happens, it can affect the engine efficiency. Okay. Because we learn from emissions, right? Deposits sometimes absorb the hydrocarbon, sometimes dissolve the hydrocarbon. Okay. So if we have deposit on the piston crown, right, we may have some hydrocarbon that left unburned, and it will come out with the exhaust. Okay. Now, to perform the effective lubrications, right, the system needs to have a good mixing between oil and fuels. Right? For this system to be effective, right, the system need to have a good mixing between oil and fuel. So this can be done either by what? Either by separating the mixings between these two, right, fuel and oil before use, right, before use it, or by adding some additive, right, to the oil, right, so that the oil, the lubrication oil here, will have a good mixing characteristic here. Okay. And since the oil have to mix with the fuel in order to perform the lubrications, right? So this sometimes may create a problem, right? For example, under some engine operation, such as what? The light load here, such as light load. For example, when the car or the vehicle moving down the hill, right? There might be insufficient lubrication that could happen, right, under these conditions, because when engine go under the light load, the amount of the fuel is less. And since the amount of the fuel is less, it will lead to less lubrication oil. And that's the reason why we don't have enough lubrications, right, under the light load condition of the engines, right? Because under light load, the supply of the fuel is less. And that means the lubrication oil is also less, right? And this last one is the major limitation for this system, right? This is the major limitation for this system, that on this condition, this system will have the problem to lubricate the engine. The next system we call is the auto lube system. Auto lube comes from the automatic lubrication system. The auto lube comes from automatic lubrication system. Right? This is the system that used mostly in the motorcycles. In the motorcycle, right? It's normally used in the two-stroke engine. So at present, we have no longer for the two-stroke engine, right? So you don't see this system anymore, but it's good to see how this system works. Okay, right. So it's used mostly in the two-stroke engine, where we have the lubrication oil stored in a separate tank, right? Not inside the engine, but in another tanks, right? The system consists of what? Consists of a nozzle spray or an oil injector, right? This is used to measure the amount of oil injected in the crankcase in every engine stroke, right? So we use a nozzle spray or the oil injector to measure the amount of the oil, the lubrication oil in the crankcase, right? And this system is more efficient than the mist lubrication system. Okay, so let's look at how this system is. Right. In this picture, you can see we have an oil tank here, right? Not inside the engine. Our engine is here. Okay, right. The system is controlled by using this handle or the handhold here, right? By twisting this handle, right, it will regulate the oil injector here, the oil injector here, with it dry by the warm dry here, the oil injector here, right? So twisting this will regulate the tension in the auto loop regulator cable, which is this one. By twisting here, you regulate the tension here, and the amount of the tension will control the amount of the oil that will flow into the engine. Okay, and when it flow in here, right? When it flow in here, right? It will flow through this rotary inlet valve that will open and close to let the oil flow into the cylinders. Okay. The amount of the fuels is also regulated by this throttle cable. There is another cable here, right here. So these two cable, the auto loop regulated cable and the throttle cable, right, are both controlled by the twisting of the handle via a single cable here, right? So these two cable will work together. One is to control the amount of fuel. One is to control the amount of the oil, right? And both will flow into the cylinder here. Okay. That is the auto loop system, right? You no longer see this system anymore, but back to 20 or 30 years is a very famous for the motorcycles, the auto loop system. Okay. The third system is called a SPAD system. This system is normally used in the engine that is under light duty and slow speed engine. Right? Slow speed engine mean what? Less than 250 RPM. Right? Less than 250 RPM. Right? So this is the kind of engine that use the SPAD system. Okay. The lubrication oil or the lubricants, right, if you see in this picture, right, it's stored at the bottom of the engine crankcase. This is the bottom of the engine crankcase. So above, right, there is a crankcase here. There is a crankshaft here at the above here, right? So it's stored below here, right? And the lubrication oil here is maintained at the constant level, right? It's always maintained at the constant level in order to ensure that there will be enough lubrication oil need for the engine under different operating conditions. Okay, so we have a storage which is underneath the engine crankcase here, right, to store the lubrication oil. So the oil now is inside the engine. Okay, for this system. Okay. This system works by using the oil pump. Right now, we need the oil pump. Right, the oil pump is here. Right, to draw the oil in this reservoir. Right, and then deliver the oil through the distribution pipe, right, into the splash trough. This is called the splash or the oil trough here. Right. Small area here, right? So the oil will be pumped by the pump and send it into the trough here, right? And this trough is located at the big end, under the big end of the connecting rod. So above here is the connecting rod, and the connecting rod have two ends. One is the big end, and on the top is the small end, right? Okay, so this trough here, or the trough here, is provided with the overflow, right? The overflow is very simple. You see this is what we call the overflow, right? So if the oil, right, go beyond this level, right, in the trough, all the oil will fall down to the oil reservoir down here, right? So we don't want the oil, right, here to fill over this level, right? or in other words, we want to keep the oil level in the troughs constant, right? Always constant. Right? After we filling the oil in the trough with the pump here, right? So the level of the oil here is always constant because of this overflow here. Okay, and we have a dipper, right? Connect to the big end or the bottom end of the connecting rod. Right? This dipper is doing what? Right? This dipper, right, will dip into the trough. Right? Will dip into the trough, and that means it dip the oil in the trough at every revolutions of the crankshaft here. At every revolution of the crankshaft here. So under these dipping conditions, right, under this dipping condition, you imagine it go up and down, right, dipping every time that this crankshaft rotates. Right. So under dipping condition here, the oil can be splashed all over the interior of the crankcase, right, such as it will splash into the piston and onto the exposed portion of all the cylinder wall. Okay. So this is how they call it. This is why they call it a spat system. Okay. The dipping oil here, after it spat over the interior portions of the cylinders, right, it will be collected in the sumps, right, where it is cooled down by the air that flowing around the sump here. Okay, so it will do this over and over, like the animation that show in here. Right, this is a dipper. Right, so it dip the oil and spat the oil to into the cylinders. Okay. Okay. Then this cool oil, after it being cooled down by the air that flow around, right, the cool oil is then recirculated. Okay. The fourth system is called the pressure feed or force feed system. Right? The pressure feed or force feed system. Right? In this system, we also have a sump, and we also have the oil pump. Right? So the oil will be drawn from the sump by the oil pump, right, through the oil stainer. The oil stainer is used to prevent any foreign particles, right, from entering into the oil circulating system, right, so that it will not contaminate our oil. Okay. And we also have a pressure relief valve that is installed in this system. That this pressure relief valve is to maintain the constant oil delivery pressure. Right? So the oil pressure will not go beyond the pressure that's set. Right? So the delivery pressure is always constant. Right? So if the oil delivery pressures go beyond the setting point, right, this relief valve will open, and then it will allow some of the oil, right, to flow back into the sumps, right, in order to relieve the oil pressure in the system. Okay, so this picture show you the pressure feed system, right? One of the pressure feed system, in which for the pressure feed system can be divided into two types. The first one we call is the wet sump, and another one we call is a dry sump. Right? This picture shows you a wet sump system in which we have an oil reservoir in the engines in the sump here, right? And we have a delivery pump. Right? This delivery pump normally not outside, right? It's normally in the sump here, right? And then is we equipped with the relief valve here, right? So that if the pressure here is greater than the set point pressure. Right? The relief valve will open and return this oil back to the sump here. Right? And at the filter, the oil filter here, we also have a bypass. We also have the bypass here. Right? In case that our filter is clogged, our engine still receive the lubrication oil. Right? So we need to have a bypass here. Right? So when the filter clogged, the oil will flow through the bypass and to the engines. Okay. Okay, this picture also shows you the wet sump system, right, where you can see that the oil now is delivered to the different part of the engine, such as the crankshaft, the camshaft, and the rocker arm here on the top here. Right. The way that the oil in this system do the lubrication is different, right? Right? When they do the lubrication for each part is different. For example, in the crankshaft and in the camshaft here, right? The lubrication oil is internally flow in the oil gallery. This is the oil gallery, right? That is inside the shaft, right? So it is internally lubricate the shaft, here, right? Lubricate the bearing on the shaft here, right? Here is the bearing, right? Yes, bearing. So it internally lubricate the bearing and also on the camshaft. Right? But for the locker arm on the top here, you can see that the oil is splashed down under the pressure from the pump here. Right? So it's splashed down under the pressure to do the lubrication for this part, or we can call it the externally lubrications. Right? So in here they do internal lubrication, and for some part of the engine they have to do external lubrications. Okay. That is the wet sump. Right? For the dry sump type, it's shown right here. Right? For the dry sump type, right, you can see that we have no oil sump in the engine. Right? The oil tank is outside. And because the oil tank is outside, we need to have one more pump. We call it the scavenge pump, that is draw the oil after lubricating the engine. Right? All the oil will be drawn by this pump and send it back to the oil tanks. Send it back to the oil tank. So the difference between the wet sump and dry sump is that we have no reservoir inside the engine, no oil reservoir inside the engine, and we have to have the external or the remote oil tanks and also another pump, right, to draw the oil from the engine back to the oil tank. The rest is the same. The rest is the same, right? And this delivery pump is also outside, cannot be inside, right? For the wet sump, this delivery pump can be inside the engines. Okay. Okay. This dry sump is normally used in the situation when the engine is run at either in the unusual or extreme conditions, such as what? Under heavy accelerations, right? For example, used in the racing car, right? Used in the off-road driving, used when you run the car to climb the steep hill, right? Very high steep hill, or even when you're running on the uneven surface. Because under these situations, right, it's very difficult for the wet sump to deal with the oil if the oil is still stored inside the engine, right? Because the oil, the amount of the space inside the engine may be not big enough, right? Especially when you use for the racing car, in which you need the high flow rate of the lubrication oil, right? So the storage inside the engine may not big enough to contain the amount of the lubrication oil that can serve such a high lubrication oil flow rate, right? That required by the racing car, right? And on the steep hill, you cannot maintain the level of the oil, right, inside the engine, right? Because it's go up the hill, right? So it's hard to maintain the level of the lubrication oil inside. And when you cannot maintain the level of the lubrication oil, right, that means you may not have lubrication oil, right? Because the pump may not be able to draw the air from the reservoir inside the engine. Okay, so that is the reasons why under this situation, right, dry pump is more preferred than the wet pump. Okay. Okay. The number five system is called the combined splash and force feed system. Right, combined splash and force feed system. This is the dual system. Why we call it a dual? Because it combines the splash system and the force feed system together. Right, and most of the car that use nowadays, right? Most of them use this system, right? So in this system, right, we have the pressurized oil, right? Because oil is pumped from the oil pump, so it has pressure. Right? This pressurized oil will flow from the oil pump, right? And then this oil will be distributed to several parts of the engine, right, by splashing from the crankshaft. Okay, so it will splashing from the crankshaft. So in here, in these pictures, right, you can see that the oil is pumped and flow into the main gallery. This is the feature of the force feed system. Right, we have an oil gallery inside the crankshaft in order to do the internal lubrication for the main bearing on the crankshaft, right? Okay, so this is the feature for the force feed system here. Okay, and then uh, oil that flow inside the gallery, right, will flow out, right? We will flow out later on, right, and splash out from the crankshaft. Right? After it's flow in the crankshaft to do the lubrication, it will splash out from the crankshaft and back to the oil sumps. Yeah, right. And the system also have a dipper. Now you see a dipper here, right? So the dipper here will do the splashing of the oil to all the engine part that above the crankshaft here, right? No matter it's a piston, the piston link, and so on, the connecting rod and so on, right? So this is what we call the combined system, because we have a force feed to do the lubrication, right, internally for the crankshaft, right? And we have a dipper to do the splashing lubrication for the external part. Okay, so it's a combined system altogether. Okay. Okay. So this picture shows you an overall picture of the lubricating system part. To summarize everything, right, we have the oil sump here, right, and we have the oil pump. We have an oil pickup screen here, right, to eliminate any dirty particle before getting into the pump. Okay, we also have pressure regulator, but it does not show in this picture, right, to regulate the pressure of the oil before flowing into the engines. Right? We have the oil filter here, the oil filter here, right? And we also have the filter bypass valve in case that this filter is clogged, right? The oil will flow through this valve, right? So it's called the filter bypass valve here, not flowing into the filters, right? And then we have a main gallery, right? Main gallery, okay, that will do the internal lubrications, right, to the engine. They do not show here the dipstick or the dipper and the pressure indicator of the oil. Right? You can see some car, they have a pressure gauge to determine the oil pressures here. Okay. So that is the lubrication system, 5 lubrication system in overall. Right? Start from very simple one, right? No equipment, no pump, no oil stainer, no oil filter, just mixing the oil with the fuel, right? And then we have auto loop system that is used for the two-stroke engine, where we have no space under the crankcase to store our lubrication oil, right? And then we have the splash system, that we have a dipper to splash the oil all over the internal part of the engines to do the lubrications. And then we have the force feed system that we use the pump. We start to use the pump, right? So we have the gallery or the piping, the internal piping for the oil, right? To do the lubrication for the main bearing, right? At the crankshaft, the bearing at the camshaft, the bearing at the connecting rod. Okay, this is the force feed system. Right? And then we have the combined system between the splash and the force feed system, right? To help do the lubrication so that the lubrication process can be more effective, right? And this is almost the last ones, right? That we cannot use the lubrication oil for a long time, not only because it exposed to the heat, right? But sometimes because it's contaminated, right? The oil is contaminated. So we have to replace it from time to time, right? Due to this oil contaminations, right? Which is caused by what? Caused by the bovine gas. Bovine gas is what? The bovine gas can be either the exhaust gas or the mixtures, right? Both of these can leak underneath the piston, right? The exhaust gas and the air fuel mixture that in the combustion chamber. Both of these gas can leak underneath the piston. And if it leaks underneath the piston, it will go to the oils, right? So this gas can add what? Fuel, raw petrol, right? Fuel and water, which is the product of combustion, to the oil, right? So it can damage the oil quality, right? So the oil, our lubrication oil is contaminated. The excess amount of heat, right, can also cause the thermal breakdown in the oil. Okay, the excessive amount of heat that happen to our engine, right, that might happen because of the improper air fuel ratio or maybe a heavy load linked on the engines, right? These are the cause of the excessive heat or extra amount of heat, right? When it happens, it can cause the thermal breakdown to our oil. Also, the high engine speed or excessive cranking, right? Or run the engine at high speed for a long time, right? It can dilute the oil with the fuels. Okay? And the cooling gasket leak, right? If the cooling gasket is leaking, right? it will ruin the oil or damage the oil, causing or changing the lubrication oil into slugs, right? Or in other words, it changing the oil viscosity, right? If this gasket is leaked, right, it will damage the oil, right, changing the viscosity of the oil. Right? And also, if you're driving the engine in a short distance, right, frequently that you drive the engine in the short distance, such as for some rich family, they have the car just to do the shopping at the market near the house. Right? So it's a short distance running for this car all the time. It can also damage the oil quality. Right? This is something that you have to understand, right? Because some family think that I do not run this car for a long distance. Why we need to change the oil, right? Right. So if you run the car in a short distance, you also need to change the oil because it can damage the oil quality. Okay, as well as if you have the extensive idling of the engine or running the engine with no load, right? It can also contaminate the lubrication oil. Okay, the cold weather engine operations can also deteriorate the oil also, right? Because the oil viscosity increase or go up as the temperature go down, right? Under lower temperature, the oil viscosity go up. Okay, so high viscosity, right, will create the problem for the engine to start, okay, under the cold weather operations, right? The tailor touring is also damage the oil, right? It damage the oil because of what? Under touring conditions, right, we have the low flow velocity of the lubrication oil, right, which is not high enough to perform the lubrication, right? Or maybe we don't have if it under throw, right? So the velocity is very important. Okay. Okay. And under the excessive heavy loading, right, and running the engine under dirty and dusty conditions, right, can also cause the oil contaminations. Okay, so this picture shows you how where the contamination can happen to the oil, such as from the dust, like that flow in with the air, from the mobile gas underneath the piston because it leaks from the top down to underneath the piston here, right? And also from the leach mixtures, that we may have the unburned hydrocarbon left over. All of this can contaminate the oil here. Okay. Okay, let's look at the example calculations for the lubrication system. Okay. We have a 4-cylinder 2-stroke cycle engine with a 2.65 liter displacement and crankcase compressions. Okay, that is running at 2400 RPM with an air fuel ratio equal to 16.2 to 1. At this condition, the ratio of the mass of air fuel trapped in cylinders after all valves are closed to the mass of air fuel mixture injected into the cylinder. So now they're talking about the ratio of these two mass. The first mass is the mass of the air fuel trapped in the cylinder after all valves are closed. That means both intake and the exhaust valve closed. Right? This is the mass of the air fuel that trapped in the cylinder that they mentioned. To the mass of the air fuel mixture injected into the cylinder. Right? This is the amount of mass of air fuel mixture that deliver into the cylinder. Okay. One is the mass that actually flow into the cylinder. Another one is the mass under trap in cylinder. In fact, it's supposed to be the same mass, but it is not. Why? Because along the way that we draw the mass into the cylinder, the intake valve open, the exhaust valve also open, right? So it's very simple that the actual amount of air, of mass that flow into the cylinder will not or does not equal to the amount of mass that is trapped into the cylinder. That's why we have this ratio. And this ratio we call it the trapping efficiency, which is equal to 0.72, right? And another ratio is what? The ratio of the mass of the total charge tapped in cylinder, including the exhaust reservoir, to the total mass of the displaced cylinder volume. Now, they talk about two mass. Right? The first one is the mass of the total charge tapped in cylinder, which is the first mass that we talk about. But remember, inside the cylinder, we also have the exhaust reservoir, because the exhaust gas do not completely fall out from our cylinder. We still have some of the exhaust that left over in the cylinder, right? So under the actual situation, what you see is what? You see mass flow in the cylinder, and you also see some mass fall out of the cylinder, right? And if you consider these two mass to be the air fuel mixture, right? The ratio between these two will be the first one, the tapping efficiency, right? And if you consider also another mass, which is the exhaust mass, right, that do not flow out, this will be the second ratio. This will be the mass in the second ratio that they talk about, which is the mass of the total charge trapped in the cylinder, including the exhaust residue. To what? To the total mass of the displaced cylinder volume. This is the physical volume, right, that you can contain the amount of mass, right, the displaced volume, right. With this displaced volume under this density, what is the amount of mass that can be contained in this volume? So they compare the first mass with this mass, and this is called the relative charge, which is 0.87, right? 0.87. The first one is 0.72. The second one is 0.87, right? And now they talk about the exhaust residue, right? They give you the information about the exhaust residue from the previous cycle in each cylinder is 7%. It's 7%. Okay. Oil is added to the intake airflow such that the input fuel to oil ratio is 50:1. This oil is the lubrication oil, right? Now, they tell you that with 50 part of the fuel, they will add 1 part of the lubrication oil to the intake airflow, right? So the input fuel to oil ratio is 50:1, right? So this is the information that they give you in these examples. Okay, they want you to calculate the rate of the oil used, the lubrication oil. Remember, every time that we talk about the oil here or we mention about oil here, it's always lubrication oil. So they ask you for the rate of the oil used. They ask you also the rate of the unburned oil that added to the exhaust flow. Okay, added to the exhaust flow. So how we can do the calculations? Okay, so we start from what they give, right? From the relative charge, right, which is 0.87, right? So by definition that they give us, right, we have the mass flow rate of the total charge trapped in the cylinder, including the exhaust residue, will be equal to what? 0.87 of the total mass flow rate in the displaced cylinder volume. This mass flow rate in the displaced cylinder volume, we can calculate from here, right? If we know the density of the air, we know the displacement volume of the engine, we know the speed of the engine, and we know the crank revolutions, the number of crank revolutions, right? In which here is the two-stroke engine. So this n, small n here is equal to 1, right? We know the density of the air, we know the displacement volume they're given, we know the speed of the engines, right? So from this, we know the mass flow rate of the total charge trapped in cylinder, including the exhaust reservoir, right? So now we use the second other information. They said the exhaust reservoir is 7%, right? So the trap charge, the total trap charge that we have, 100%. 7% is exhaust reservoir. So only 93% of the trap charge is the air fuel mixture, right? It's only 93% of that is the air fuel mixture. So we will, that means what? That means this number, right, which includes the trap charge and the exhaust reservoir, right? If we want to know how much is the air fuel mixture, right, then we have to time this number with 93, right? So that we will know the mass flow rate of the air fuel that trapped in the cylinder after all valves are closed, right? Now you see the relation between these two mass. You see the relations. Okay, so this is the mass flow rate of the air fuel trapped in the cylinders. Okay, and then we go back to the information that we get from trapping efficiency, which is what? 0.72, right? So we can find out the mass flow rate of the air fuel mixture that injected into the cylinder, that actually flow into the cylinder, which is what? This number divided by 0.72. So this is the actual amount of the air fuel flow rate that flow into the cylinder, but it only trapped in the cylinder for just this amount, right? Because along the way that flow in, our intake valve open and our exhaust valve also open. So some of this air fuel mixture might flow out with the exhaust air. Okay, that's why these two amounts, they are not the same. Okay, so now we know the total air fuel mixture that delivered to the cylinder. And then we use the air fuel ratio 16.2 to 1 to determine the rate of the fuel input. Right? Because we know the air fuel mixture already, this is the total. Right? So with the air fuel ratio 16.2 to 1, that means what? In total of 16 to 1 plus 1. For 16 to 1 plus 1 part, which is equal to 17.2. This 17.2 is equivalent to 0.1407 kilogram per second, right? So, and fuel is just 1, right? So we divide this 0.1407 by 17.2. It will give us the rate of the fuel input, right? And with the rate of the fuel input, we now know, we already know that the input fuel oil ratio is 50 to 1, right? So the oil input will be what? This number divided by 50, right? Because 50 to 1, right? So this number, which is the oil, the fuel input divided by the fuel input 50, will be this. And this will become the oil input because it's 1 for every 50, right? So it equivalent to what? 0.95 kilogram per hour or 0.67 liter per hour. Okay, so this is the first answer. The second answer, since the 72% of the oil is trapped into the cylinder and burned, right? Then 28%, right, enter the exhaust during the valve overlap period and left unburned, right? So this is the total amount of the oil input, but only 70% of this oil is trapped, right, and burned. Another 28 flow out with the exhaust because it comes in the same time that the intake and the exhaust open. Okay, so that means the mass of the unburned oil in the exhaust will be what? 0.95, this amount, times with 0.28, right? So we deliver 0.95 kilogram per hour of the oil, but 0.17 kilogram per hour of the oil flow out with the exhaust gas. Right? All of this happened because of this valve overlap, right? So in valve overlap period, this is the physical event that you should be able to see, right, for the mass in and mass out. Okay. 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 So that the example calculation of the lubrication oil, right, that involved with the oil, right? Okay. Let's look at the lubrication oil ingredients, right? The basic ingredient in most lubricating oil are the hydrocarbon that make from the crude oil, right? And this table shows you that, right? On this column, this is the name of the lubricating oil or the lubrication oil. Right? It goes by number. We will talk about this number later on. Okay, and with different number, they have different number of carbon in their component, right? And the number of carbon is higher by number. Is the number increase, you can see the number of carbon increase in here. Okay. So different lubrication oil will have different number, different amount of the carbon here. Okay. Now, in order to improve the quality of the oil, we cannot depend on only the hydrocarbon component in the lubrication oil. We need to add other ingredients into the oil. Right? So by doing this, if we add some additive or some ingredient into the oil, the engine performance and the lifetime of the engine can be increased. Okay, so this is the reason why we have to add some ingredient or some additive into our lubrication oil. The additive that we add into the lubrication oil are what? The first one is the anti-foam agent or anti-foam additive, right? This additive is used to reduce the foaming that would happen when the crankshaft and other engine component loaded at high speed in the crankcase oil sump, right? Because remember we have a dipping actions, right? So the foaming may occur, and we don't want that foaming to occur because we may have oxidization happen. Okay, so we have something to reduce this foaming, like by adding the anti-foam agents. Okay, the second one is oxidation inhibitor, right? To eliminate any oxidization or oxidation that happen, right? Because of what? Because when foaming occur, right, the oxygen is trapped, will be trapped in the oil, right? And it will lead to possible oxidations of the engine component. Right? If the oxidation happen to the engine component, what come out is what? Rust. Rust will come out in your engine components. Right? So we need to add the additive to inhibit the oxidation. Right? Such additive, right, is called zinc ditriophosphate, ditriophosphate, right? So in the lubrication oil, we add this additive to prevent any oxidation that will happen, right? So rust cannot happen to our engine components. The third one is the porpoise depressants, right? This additive is to reduce the temperature at porpoise, right? We reduce the temperature at porpoise, right? So that our oil can still flow easily under extreme conditions, right? Under extreme conditions, it can flow easily, right? Not hardly flow, right? If the oil can hardly flow, right, the lubrication will not happen. Number four is the anti-rust engine. Apart from the oxidation inhibitor, right, we also add the anti-rust engine to prevent rust in the engine component. Number five, detergent or the cleaning agents. Right. This agent is used for cleaning the engine components. Right. It's made from the organic salts and the metallic salts. Right. It's help cleaning by what? By suspend the deposit. Suspending the deposit, it means we don't allow the deposit to happen. And also the impurity, no impurity. Right? And stop the reactions that will form varnish or dirty surface on the engine components and other surface deposits. Right? So in overall, it helps eliminate the deposit and impurity that might collected on the engine surface, engine component surface. Right? Apart from this, it also helps to form neutralized axis, form the sulfur in the fuels. Right? If our engine has sulfurs, right, it may react with the oxygen to be the sulfuric axis, which is the axis. So we have to add this detergent to neutralize this axis from the sulfurs. Okay. Anti-wear agents, right, to prevent any wear that happen to our engine component. Friction reducer to reduce the frictions, right? So engine part can move smoothly. Okay. The viscosity index, right, improver to increase the viscosity of the lubrication oil. Okay. So this one will tell you how to name the lubrication oil, this slide. Right. According to the SAE standard, right, SAE stands for Society of Automobile Engineer. Right. According to this standard, the lubrication oil is run by number. It's run by number, right? So every lubrication oil will have number, right? In which the small number mean less viscosity, right? You can see SAE with small number will always have less viscosity. Okay, so oil with small number, right? For example, SAE 10, so here, right? Oil with small number is normally suited for cold weather operations, right? In order for the viscosity not to go too high under cold weather or low temperatures, right? Because the temperature is already low already, right? So you need to go for the oil that already have low viscosity, because if the temperature go up, it will have, if the temperature is too low, it will even lower down the viscosity, okay? And the oil with higher number, for example, the SAE 50, right? This is a more viscous oil, right? And more suitable for use in the modern high temperature, high speed, and cost tolerant engines, okay? Because the tolerance is very, very small, right? So you want to reduce any frictions anywhere that might happen, right? So you need more viscous lubrication oil in order to do this. Okay, so from this picture here, right, as I already mentioned, the oil with higher number will have more viscous than the oil with lower numbers. The viscosity is higher. Okay, there is an attempt to reduce the variation of viscosity, right? As you can see, right, it changes with the temperatures, right? And it means if you look at our actual engine operation, right, the temperature can be varied, right? So they want to reduce the variation of the viscosity with the temperatures, right? This can be done by what? By using the multi-gate oil, not a single gate oil, right? If we see SAE follow with the number, nothing else, this is called a single gate oil, right? So to reduce the variation of viscosity with the temperatures, right, they use the multi-gate oil, right, by adding what? The polymer into the oil, so that we can keep the viscosity more or less constant, right? It's not totally constant, but it less slope or less change over the operating temperature length of the engine. As you can see here, right? The dotted line represent the multi-gate oil, right? For the single oil, you see a sharp decrease, which means the high slope, right? But for multi-gate oil, the slope is less. So a small decrease compared with the change of the temperature. This is what they call keeping the viscosity more constant, right? Not totally constant, but more constant, right? The multi-gate oil, right, normally named by two numbers, right? For example, this SAE 10W, that's 30, okay? It means the oil has the property of 10 viscosity when it's cold. The W stands for winter. And when it's hot, the viscosity become 30, right? So the viscosity only change in this small length, 10 to 30, not in the wide length, right? Change only in this small length. This is what they call more constant, okay? So I think this is it, right, for these lectures, right? I combined 2 weeks to lecture together into 1 week lectures because I would like you to have 1 free week to prepare for the final exam. Okay, so that's the reason why I combine these 2 lectures together. And next week, right? Which is a holiday. Okay, next week is a holiday. I will give you video, the lectures, the lecture video, so that we can keep up with the time that we have. Okay, so that the last week it's gonna be free for everyone to prepare yourself for the final exam. Okay, so any questions for these lectures? Any questions? The friction and lubrications. Only 6 students. Only 6 students. Any questions before I finish my lectures?
ไม่มีครับ
No, no questions. Okay, good. Okay, so next week is a holiday. We will see you. I will see you week after next week then. Okay, so bye bye everyone.
ผมครับ
ครับ
ขอบคุณครับ